In the second video for 6.2a, we'll finish up integrating trigonometric integrals. And now we're looking at integrands of the form secant to the power of n of x times tangent to the power of m of x for a whole number of positive powers n and m, just like sine and cosine. We need some preliminary integrals before we get started, but a good bit of this is going to follow like sine and cosine did. To get started, we should recall the integral of tangent of x. This was actually done in Calculus 1, and we see here that it's actually performed with a u substitution. The first step would be to rewrite tangent of x as sine of x over cosine of x. That's a trigonometric identity, or possibly even the definition of tangent in some cases. And we have an integral that looks like sine of x over cosine of x. We realize that the sine of x is the derivative of cosine of x with a minus sign missing, but that's always easy to add. And so we make the u substitution, u equals cosine x, and du becomes negative sine x dx. We see that sine x dx is equal to negative du then. And then the cosine x in the denominator becomes u. And then we have the integral, negative integral of 1 over u du. That's negative natural log of u plus c. Substitute that in for cosine of u for cosine of x. And lastly, we realize that a multiple times natural log becomes an exponent of the argument of natural log, which is cosine of x to the negative 1, as we see here. Cosine x to the negative 1, remember, is not arctangent, arc cosine, but it is 1 over cosine, and 1 over cosine is the secant of x. So again, that's a Calc 1 problem. You can look back in your textbook for integrals of or antiderivatives of trigonometric functions, and you should find the same exact problem there. It's worth knowing how to do if you don't, but typically probably just remember the antiderivative of tangent of x as this. Okay, next, recall the integral of secant of x. Well, actually, maybe we've never seen this before. This is a very tricky u substitution to make, and we'll do it here. So students are not really responsible to come up with u substitutions that are so complicated in this class, but once we've seen this, you should be able to come up with the integral of secant of x either from having it written down or just recalling it from memory, or in a worst case scenario, deriving it as we do here. So the step to come up with this antiderivative, or the steps to do it, is the following. We take the integral of secant of x and we multiply it by a form of 1. We'll see why momentarily, but this is a form of 1. Tangent x plus secant x over itself is 1. We do this, we don't try to simplify anything. We multiply this secant of x times the terms in the numerator to get what we have in the line below. So we have secant x times tangent x plus secant squared x, or secant x times secant x. Those are our two terms in the numerator. Now, let's connect that to the denominator in some way. If we look in the denominator, we realize that the derivative of tangent of x is secant squared x. Similarly, we realize that the derivative of secant of x is secant x tangent x. Okay, so that means that the derivative of tangent x plus secant x, as we've got it written over here as u, is actually equal to exactly what's in the numerator, secant squared x plus secant x tangent x. So we've got a very nice u substitution set up with this sort of complicated looking integral. In the end, if we let that denominator be u, du is in the numerator, and we'll have exactly this expression in our integral. That's very easy to integrate. We just have the natural log of u plus some constant. And to fill in for u, we'll put u as tangent x plus secant x, and we get the statement we've got down at the bottom. That's the antiderivative of secant of x. Notice it's very similar to the trick that we used above for sine of x over cosine of x. U is equal to the denominator, and we have du in the numerator, or something that looks close enough to it that we can make it work. And that's exactly what's happened here. Now, of course, the crux is to think of something like this. For a good challenge for students, cosecant, the antiderivative or the integral of cosecant is done in a very similar way. So try that out. It's going to involve cosecant and cotangent. See if you can derive that one on your own. If not, I think the book includes it somewhere, or of course you can find it in another resource. Now, lastly, let's see one more integral, the integral of secant squared of x dx. Now, you might pause on it if you didn't see the answer below and wonder, what is the antiderivative of secant squared of x? Well, hopefully you'd eventually bring it back around to calculus 1 and remember that the derivative of tangent of x is secant squared x. So, of course, the antiderivative of that integral is given below as tangent x plus c. So it's a useful fact to not forget, because when we get into the details of these problems, we might overlook something nice like that. Okay, so those are some preliminary integrals. Now we know that if we reduce an integral down to the integral of just tangent x or secant squared of x, we can pop out with an antiderivative and be done with that portion of the problem. So let's see this in practice. So we start with odd powers of tangent and secant, or at least one of them being odd. In this case, they both are. Now, if they're both odd, we can do something pretty nice. We will peel off a factor out of tangent cubed and one factor out of secant to the fifth to get tangent x times secant x. And that's what we have highlighted off to the right here. It's reduced the cube to a square and it's reduced the fifth power to a fourth, respectively. And we see tangent x secant x, and we have to remember why that's useful. Tangent x secant x dx. So as always, we're trying to build a useful du, a useful derivative for a u substitution, for some u. Okay, well, tangent x secant x is the derivative of secant x. We see that starting to happen down below. So this suggests then that if we get everything that isn't part of that du to be in terms of secant of x, then we can make a u substitution secant x and simplify this expression overall with a du off to the right. And so that's exactly our goal. And we realize that, well, secant to the fourth x is already in terms of secant of x. So that's fine. That'll work out with this du off to the right. Now, tangent squared x needs to be changed. Well, in order to do so, we use the Pythagorean identity for that. Recall that the first page of these notes has exactly this Pythagorean identity for us, or one similar enough to it that we can solve for tangent squared x. And we make this substitution. Now this is in terms of secant of x minus 1. And when we make our u substitution, here is a decent place to do that. We have u squared for secant squared x minus 1 times secant to the fourth x is u to the fourth. And now we just carry out the distribution of u to the fourth times u squared minus 1 before we integrate to simplify our integrand. We have u to the sixth minus u to the fourth for both of these multiples. And that's a simple antiderivative. Remember that du is this term here the whole time, so this term becomes this du down below. So we're all set to integrate. And power rule gives us 1/7 u to the seventh minus 1/5 u to the fifth plus c. And we need to reverse our substitutions. U is equal to the secant of x, so u to the seventh is secant to the seventh x, and similarly for secant to the fifth x. So to recap, the main point of the strategy is if we have odd powers, let's try to peel off a factor out of each of them, form secant x's derivative, call that du, and get everything else to be in terms of this variable u, which is secant of x, or in other words, get everything in terms of secant and make the u substitution. So it's encouraged that students try to do these problems immediately after seeing an example like this. So you could get a blank page, pause the video, and try this problem from the top without referring to this, just to see if you're starting to catch on to how the method works. It's a great way to test yourself as we go through these problems. So let's see what's next. We've got even powers of tangent to the fourth x and secant to the fourth x. And we realize that this, in sine and cosine, this can really be a long process. We were replacing things with Pythagorean identities, expanding that, and then possibly replacing with more Pythagorean identities and expanding from there. So that can be quite a mess. Turns out tangent and secant are a little bit nicer in this regard. So in this case, when we have even powers of these functions, or even powers of secant might be the thing that we really want to consider or think about. Well, let's peel off secant squared of x out of secant to the fourth x. We still have secant to the fourth x in our integral. It's just we've written it in this decomposition here. Secant squared x dx. We want to consider that as possibly du for some substitution u. we're always kind of working backwards. We sort of pick what we'd like to have for du, and then we check to see whether or not it's useful. So if this was going to be a du, we ask ourselves, what works, or will it work for some u? And in this case, it does. We see off to the right, and maybe after some thinking, we realize, if u is tangent of x, we know that the derivative of tangent of x is secant squared x. It might be nice to have a table of these derivatives and antiderivatives for simple functions lying around so that we can sort of explore our way through these problems and check these things quickly. So if that's the case, then perhaps a u substitution of tangent x will be useful in our problem. And this term, secant squared x dx, can be du. We look off to the right and realize, well, this is already in terms of tangent, so that would be u to the fourth. So that's great. Secant squared of x, it's not in terms of tangent, but since that's an even power, we can convert it with a Pythagorean identity to be in terms of tangent. And that's exactly what we do below. Secant squared x becomes tangent squared x plus 1. Now, u is equal to tangent of x. So each of these tangents is replaced with a u to their respective powers. dx, or du in this case, is secant squared x dx. So this is swapped for this. And we're off and running again with another power rule antiderivative. And in the bottom, we have 1/7 tangent to the 7th x plus 1/5 tangent to the 5th x. Of course, there's some details in the middle, but that's just power rule, antiderivative, and backing out of our substitution. So even powers don't turn out to be too bad. Now, maybe if this was a little larger, and this happened to be to the 4th or the 6th, then there'd be an outside exponent of squared or cubed. We'd have to carry that out. But then again, it might not be the end of the world. It's just a binomial expansion. So those are two even powers for tangent and secant of x. And what else can we get into? Just in case we see some odd powers here, this should sort of give us a basis for any of the odd power cases or mixed odd power cases. We have tangent cubed x. It seems like we don't have secant around to help us out. So as we enter into this one, we decide, let's split up tangent cubed x as tangent squared x, tangent of x. And again, this is possibly trial and error for students in the beginning. There's not so much an algorithm to this as there is just an instinct or an intuition. We turn that into some square of tangent because we know that we can use the Pythagorean identity to relate it to secant. And then we search around for something that might be helpful to us. Well, we notice in this expression, -1 times tangent x, that'll split as its own integral. That's all fine. We can take care of this antiderivative of tangent of x. We've done that on a previous page. It'll look like that. So we can dismiss that. If the thing to the left looks manageable, this term times tangent of x given below, if this integral seems doable, then we're all set. So having a good look at this, secant squared x tangent of x, well, we peel off a copy of secant of x and we place that next to tangent of x. So secant squared x is still in our integral. It's now written as secant x times secant x tangent x. And we realize that this is a great du for u equals secant x. So here's our u of secant x in the beginning of the integral, this one, and our du is secant x tangent x. So this is a nice clean u substitution. It might take some time to practice these and sort of see them while you're working on them, but that's what the homework's all about. So we have integral of u du after this u substitution. Of course, this has already been handled, and that's 1/2 u squared, and we back out of the substitution with u equals secant x, and it's 1/2 secant squared x minus natural log secant x plus our constant. So that is tangent cubed, antiderivative. Now let's see what we can do for integral of secant cubed. And we get a nice hint in this problem. We might need to use integration by parts. Maybe we'll always have those hints, maybe not. But we have lots of tools. It's not a bad idea to try to use them. Remember above, the first one was just u substitution. We just had to find it or see it. Now next is u is equal to, so with this secant cubed x, let's try more or less what we did the first time. Let's factor the integral or the integrand into secant x times secant squared x. And we might not have jumped straight into an integration by parts yet, especially if that hint hadn't been there. But what we'd realize, hopefully eventually, is that secant squared of x is the derivative of tangent of x. So it's easy to integrate secant squared x, and we'll get tangent of x. So it's a great candidate for a dv. So dv is secant squared x means v is tangent x. Now, off to the right, u equals secant of x. Well, this is a manageable derivative. The derivative of secant x is secant x tangent x. So u du seems to work out. Now, this is all fine. This is good. What you wouldn't want is to possibly integrate secant x. So if you placed a secant x instead of secant squared x here, then you'd have natural log of secant x for v, and that's probably complicating the integral more than you want. It's probably not the right way to go. So that's just a hint as to how to guide yourself through these. Now, integration by parts formula says the integral is u times v, so that's this term, minus v du. So v du is this expression here. And we pause and have a look at this and realize, well, there's not anything we can do immediately to it, but we realize that tangent squared of x is 1 plus secant squared of x, or 1 minus secant squared of x. Or secant squared of x minus 1, that's what I'm looking for. Both of these are subtracted. So secant squared x minus 1. So this stays a minus. It's secant squared, so it's this secant times I need to write this in so we can see it. So we have this integral on the right here is a negative secant x times secant squared x minus secant x dx, and each of these is a dx. So we split that into, because tangent squared x is secant squared x minus 1, and actually this needs to be a plus because it's a double minus, so there is a small little mistake in there to handle as we work our way through. So what we have as we complete this now is the integral of secant cubed x, which is exactly what we were trying to find to begin with. So that's I, and we'll replace that with I. And then to the right of that, we just have plus the integral of secant of x. Well, plus the integral of secant of x is plus natural log secant x tangent x. We've added I, this term, to both sides. So we have 2I on the left. And now to solve for I, we just divide by 2 and multiply by 1/2, and we arrive at the answer we have down here at the bottom. It's a good thing we caught that sign error, that plus or minus sign error. So good. That is the last of the tangent and secant examples. One other expression we might be able to see, we might come across is sum identities, sine of mx times cosine of nx. Now these are multiples of the argument of sine and cosine, not powers of sine and cosine, so it's important to see that distinction. And in this case, if we have something that looks like this, we can split it up into the sum of sine of a minus b plus sine of a plus b in this case, and similarly for the other two cases. So the idea is to move from the left side to the right side in these identities and simplify an integral that looks like this to something that we can actually manage. After all, when we see this integral, we realize there isn't a straightforward way to integrate that. We don't see a u substitution. We don't see a general integral that works here. But in these cases, it's really pretty straightforward. We just use one of these sum identities, which we should probably keep handy, maybe less so than the others at the beginning of these chapter notes, or these sections notes. But still, it's something to recall. So we'll use part 2 down below. We have sine 3x and sine 2x. I've switched the order just to make things a little bit neater on the right-hand side. So our sum identity tells us that we'll have cosine of a minus b of this minus this, so 3x minus 2x. And then the identity says that it's minus cosine a plus b, so minus cosine a plus b, 3x plus 2x dx, and everything's multiplied by 1/2. We've done that outside of the brackets that we've got. So there's that 1/2 factor from the formula. And one of these simplifies very nicely. We have just integral cosine x dx. The other one leaves us with cosine of 5x, and that can be managed through a u substitution, but we'll end up with a factor of 1/5 popping out of there, and our antiderivatives in the end will look like this, of course, with a constant of integration c added to it as well. So that's the sum identity scenario. Those are a little bit easier. They're not as common. We won't need to integrate as many functions. We won't see many integrands that look like this in the rest of the course, but it is nice to have seen it once or twice. You might see it later on in a Fourier series in another course.